Welcome to Gram-Schmidt and least squares. Let's start out with a review. If W is a subspace of Rn, the ODT, orthogonal decomposition theorem, says that if U1 through UP is an orthogonal basis of W, then each Y in Rn can be written uniquely as Y equals Y hat plus Z, where Y hat is in W and Z is in the orthogonal complement of W, that's W perp. And the formulas are, you should pause and see if you can fill this in. Y hat is equal to Y dot U1 over U1 dot U1 plus dot up to Y dot UP over UP dot UP, and Z is Y minus Y hat. The closest point in W to Y is the orthogonal projection of Y onto W, that's Y hat, and the distance from Y to W is the length of Z. All right, this theorem depends on having an orthogonal basis of W. And so Gram-Schmidt tells us that we can always find an orthogonal basis. And actually, Gram-Schmidt tells us how to find an orthogonal basis. If you would like an orthonormal basis, the last step in Gram-Schmidt is just to normalize the vectors. So I've only given the formulas in the case that you have 3 vectors, but you can generalize this. We'll never do more than 3. In our exercises, we start out by letting V1 equal X1. V2 is going to be X2 minus the projection of X2 onto W1, where W1 is the subspace spanned by V1. And then you continue this process, and you can read through those formulas. So let's look at an example, and we'll use this example in a couple minutes. Find B hat equal the projection onto col A of B. So we've got a vector B, and we've got a matrix A. Col A, recall, is the space spanned by the 2 columns of A, which I'm calling X1 and X2. Now, if X1 and X2 were orthogonal, we could just use the ODT to find B hat. But they're not, so we're going to turn X1, X2 into an orthogonal basis. So let's start out. We're going to let V1 equal X1, and that's 2, 0, 2. I'm changing over to linear format. All right, and then V2 is X2 minus X2 dot V1 over V1 dot V1 V1. All right, X2 is 0, 1, 2, and then we're going to subtract X2 dot V1 is 4, V1 dot V1 is 8, and I multiply that by V1, which is 2, 0, 2. So that's 0, 1, 2 minus 1, 0, 1, which is negative 1, 1, 1. So my orthogonal basis now for col A is V1, V2, which is the set 2, 0, 2, comma, negative 1, 1, 1. Okay, now I've got an orthogonal basis for col A, and I can simply find B hat using the orthogonal decomposition theorem. And here's my formula for the projection of B onto the column space of A. So let's start computing. B hat is B dot V1, and I've got V1 and V2 up here. So B dot V1 is 8, V1 dot V1 is 8, and that's times 2, 0, 2. And then this is a typo. B dot V2 is 4, V2 dot V2 is 3, and that is times V2, which is negative 1, 1, 1. So that's 2, 0, 2 plus negative 4 thirds, 4 thirds, 4 thirds, which is equal to 2 thirds, comma, 4 thirds, comma, 10 thirds. Okay, so now the fun part, the least squares problem. As we know, not every linear system is consistent. Here's an example of an inconsistent system. And in this case, the A and the B are the same as they were in the last example. There is no vector x such that AX is equal to B. So let me just jump down here to my picture. Solutions of AX equal B only exist for B that lie in col A. So if we take the projection of B onto the column space of A, that's B hat, which we computed in the previous problem, then we can solve the equation AX hat equals B hat. That's called a least squares solution. Now it's called a least squares solution because this dotted line here, the distance between B and B hat, is equal to the length of B minus AX hat. And when we minimize a length, we minimize a sum of squares. Now you might just say, well, we already found B hat, so why not just take the augmented matrix A, augmented with B hat, reduce, and find a solution? Okay, well, the answer to that is that required quite a bit of work. First, we had to find an orthogonal basis for col A. Then we had to go ahead and use the ODT to find B hat. There's a quicker way, and it's called a least squares solution. And here it is. So to solve the inconsistent system, AX equals B, you're going to solve the normal equations, which you find by multiplying both sides of AX equals B by A transpose. And I've got an explanation of where that A transpose comes down here, where it comes from. There might be more than one solution. If there is, then any solution is called a least squares solution. And the least squares error is that quantity length of B minus AX hat. Okay, so let's go back to our example from before and find a least squares solution. So this is also a little bit labor intensive. So I've gone ahead and I've done the grunt work for us. I computed A transpose A, and I get this matrix. I computed A transpose B, and I get this vector. And so then to solve the normal equations, what I want to do is augment A transpose A, that X should be gone. I'll take it out before I post these. Augment the A transpose A with A transpose B and reduce. And I did that, and I got this matrix here. So that's giving me the least squares solution. My least squares solution is X hat equal to 1/3, 4/3. This is the least squares solution. Now let me just show you a picture of what we did. Here's col A. X hat lives over here, all right? And then B is up here. This plane is col A. AX hat lives in col A, and it's the closest point in col A to the vector B. Now let's compute the least squares error, which is this distance between B and AX hat. So the first thing we have to do is find AX hat. Now we already know AX hat is B hat, and we did this on the first page. That's this vector here, but let's just confirm. So I take A and I multiply by X hat, and indeed I get the same vector that I got by using the ODT. So it's a different way to get the same vector. Then I have to compute B minus AX hat, and I went ahead and did that. And so the least squares error is going to be the length of this vector, which is 1/9 plus 4/9, and then 1/3, negative 1/3 squared is 1/9, which is the square root of 6/3. Now this is just an overview of least squares, but I want to just point out a pretty cool application to least squares, application to statistics. If you've taken statistics, or even if you haven't, you've probably heard of the line of best fit. So if you're given a bunch of data points and you want to find a line that most closely hits each data point. So what you want to do is minimize these errors. And what happens is, well, it depends on the course you took in statistics, but you either use computer software to find the line of best fit, or you were given some pretty gnarly equations to find the line of best fit. And what I did is I just went through and I verified that using a computer application to find the line of best fit gives you the exact same result as if you were to grind this out by hand and solve the normal equations. And I'll just let you read through that at your own leisure. And that is the end of this section.